So I believe that is time to start. We still have not so many attendees as the registered participant, but the event is going to be a long one with many very interesting interventions, so we cannot postpone the start too much. So allow me first of all to thank you for joining this event, this virtual event. At CEPS, we are very proud to host it because we believe that this topic is really forward-looking and central in the European Green Deal. Today, we will try to discuss both the technical and the economic aspect of the solar fuels value chain. The morning session will be dedicated more at the technical aspects, while in the afternoon, we will focus more on the economic aspects. I'm very happy to moderate this morning session, and I'm very glad to welcome all the distinguished speakers that will participate this morning. Just to give you a quick overview of the agenda, we will start with a welcome address by Philip Schild and Thomas Schlecker from the European Commission. Then we will leave the floor to Professor Sophia Hausner from the École Polytechnique Fédérale de Lausanne that will give us a keynote speech. And then we will ask Joachim John from IMEC, a member of our team, to provide the first presentation focusing on the solar fuel value chain. Joachim will mainly focus on the electrochemical and chemical pathways. We will have then a Q&A session for all the attendees to ask questions. A short break. We cannot serve you a coffee because a virtual event still does not allow for this, but we hope that you can get a good one. And then we move to the second part of the meeting with the presentation by Alessandro and Andrea from RINA on the thermochemical and biochemical pathways, followed by a Q&A. Finally, an high-level speech by Deepak Pant, senior scientist at Vito, and Thomas Schlecker from the Commission will provide the concluding remarks for the morning session. Before starting giving the floor to Thomas and Philip, I would like to remind you some basic rule of conduct for this meeting. So first I would invite all the participants, both the panelists and attendees, to display the name, surname, and organization they belong to. This is possible by using the rename function in Zoom. So you go on the participant panel, and then near your name, you can click on the rename button. We will take care also as CEPS to remind you about this. For us, it's very important that we are all identified. Participants that will not agree to be identified will be asked to leave the meeting. Another important rule is about the Q&A. We will answer all the questions that will be written in the Q&A box. So all the participants can write down the questions, and we will take care of answering the question during the Q&A session as much as possible. And those questions that we are not able to directly answer during the Q&A will be answered by the speakers in written form in the chat even after the Q&A session is concluded. If you have any technical question on the functioning of Zoom or on technical issue you're experiencing, you can use the chat and either address the question to the panelist or to a specific participant. You can refer, for instance, to me or to Rado, our IT manager, who is also attending this event. Finally, one important disclaimer: the event is live streamed on the CEPS YouTube channel and will be made available for later view on our YouTube channel. So by attending this meeting, you approve that the event is recorded and made available online. If you have any concern about this, you can contact the team at the address which is showed on this slide. and you can also see more about our privacy policy at the link that we provide in this specific slide, or feel free also to contact us in the chat. So now, without further ado, I would leave the floor to Thomas Schlecker and Philippe Schild from DG Research of the Research and Innovation of the European Commission to provide a short welcome address. Thank you very much.
Thank you, Felice. Philippe Schild speaking from DG Research and Innovation at the Commission. So I will start the welcoming part from our side. So first of all, well, welcome to this virtual event. I think this is sort of a series, it was a follow-up of a series of events, very important for us. And this study that has been done, and Thomas will speak a bit more on it, is very important for us. Especially in the context of the Green Deal that was sort of launched and announced by our president at the end of last year. And I would like to remind you sort of the principles of the Green Deal and why we think that those technologies that you are looking at are very important. We are looking at protecting our planet and our shared environment. We are looking at an ecological transition with opportunities for growth and economic, long-term economic positive influence. We are also looking at a real step change on the way we are using and producing energy. So, and we see this as very important. Very recently, you may be aware that sort of the Commission has published on the 8th of July a communication on the EU energy system integration strategy, where we are pushing forward the idea that from a very linear way as our energy system is constructed at the moment, going from energy producing to energy use, that we are going to a much more integrated approach, where circularity and efficiency of the system is looked in more details, like when we can use waste energy from one system to be used as an input energy from another, to look at having a much cleaner power system and a much cleaner fuel system. And we do see this solar fuel technologies to be a potential game changer. Obviously, there is a lot of potential, a lot of hope from our side, and I think from every side. So this aspect of the value chain for us is important because we want to look at the full circularity of the system. I will not take more of your time because you have quite a packed agenda. So let me again welcome you to this online event and wish all of you a very intense and insightful sessions ahead. Thomas, if you want to say something.
Yes, good morning. I think my video started also. So good morning, everybody else from my side. My name is Thomas Schlecker. I'm Policy Officer in DG Research, a colleague of Philippe, and also Project Officer of this study. So Philippe mentioned you what is the policy background and indeed the big hopes we have in this study on solar fuels research and invest, defining and developing the global solar fuels value chain. And here we look at techno-economic analysis of the pathways for sustainable implementation. So for energy transition and the ambitions we have to become a climate neutral continent, we need, beyond strong electrification, also renewable carbon neutral fuels. And here solar energy can play a game changer role, as Philippe mentioned, as solar energy is the most abundant renewable energy source. Now, in this study, we want exactly to combine understanding of the state of the art, where we talk here about technologies which are in part, at least also at a very low TL level. So a big work is already, let's say, the definition of solar fuels in scope here, as well as the analysis of what are the respective programs in place to really get a better understanding of the wider technological portfolio. And based on that, then also to develop a technology roadmap based on a value chain understanding, because things, of course, to be successful need to go to market. And here we have a vision up to 2030 and 2050, but also actually really a longer term market outlook. The aim of this study is also to establish a worldwide communication network, which is aligned with Mission Innovation Challenge on converting sunlight, and this is the Solar Fuels Forum. And to get a better understanding, of course, how we also can internationally cooperate on these technologies. Now, this is the final conference of the project, and I welcome you all on this Solar Fuels Research and Invest conference conducted by Ernst & Young and study partners of this project. And I'm very much looking forward to interesting presentations, speeches. Then we have a panel discussion also about the involvement of industry and importantly on the results of the project. So welcome to everybody.
So thank you very much, Thomas and Philippe, for this policy background and for remarking the centrality of this project for the green energy transition in the EU. I will now ask Sophia, Professor Hausner, to start with their keynote speech. There will be no Q&A after the keynote, but feel free to start writing question in the chat, in the Q&A box, sorry, and we will answer those questions in the Q&A after the presentation from Joachim. So thank you again.
Yeah, thank you, Felice, for the introduction. Welcome, everyone. From my side, I want to start by thanking the organizers, CEPS, Ernst & Young, IMEC, and RINA, for inviting me to give this keynote and effectively take you on our journey to develop a technology and scale this one for the production of solar fuels. My name is Sophia Hausner. I'm an associate professor at EPFL in Lausanne, Switzerland. So let me just start by sort of setting the stage and looking at different ways how you can make solar fuels. The idea is that you take rather abundant components such as water, and then you can either go a thermal way and do things like solar thermochemistry, solar thermolysis, or even a hybrid approach where you bring in some carbonaceous material to do solar cracking and gasification and whatnot. Or you can take a photo-driven approach where you use the photon energy, typically in combination with semiconducting materials, to produce fuels by photocatalysis, photoelectrochemistry, and so forth. And also there is the possibility for hybrid approaches where you bring in carbonaceous material to do, for example, photorefining. The fuels and, in fact, chemical commodities which you produce can be hydrogen, can be CO, and even beyond. And then, of course, you can imagine that you start to combine the approaches with high temperature electrolysis, for example, photo-driven, and you start to also enter a more interesting combined space. You can see a bit the difference between the approaches, which you can mostly characterize by temperature. So you see that the thermochemical approaches typically use rather high temperatures, while photo-driven one, typically you try to stay rather close to environmental temperature. I would say the approaches where you have biomass or fossil fuel sort of hybrid systems to us are midterm approaches and on the path towards a more sustainable, a pure solar pathway in the future. In the last 5 years, we had activities actually on these high temperature electrolyzers, photo-driven, and also on these photoelectrochemical systems, where I put our reactor, you can see here, sort of in between traditional photoelectrochemical devices and integrated PV plus electrolysis devices. And this is what I will focus today on. So I'll not talk about our journey on the high temperature electrolysis. I rather focus on our journey on photoelectrochemistry. So if you think about your path or your approach to a device for photoelectrochemical fuel production, particularly a practical device, you have to keep in mind that, of course, performance is important, technology is important, but you have to ensure that you're actually taking a holistic way or approach to it, and not only looking at performance, but also cost, sustainability, and more broadly lifetime, which has, of course, a performance component. It's related to degradation, but not. So you have to be in this sweet spot in the middle here of this flower of at least these 4 components to consider. And it also requires that you go for an approach which allows you to be scalable, because here we're dealing with terawatt scale problem. And of course, cost is one way to approach scalability, but not only. And so if you start to think now, I want to make such a device, the initial questions you would have is, what would be the best material combination for such a device? What would be the best architecture / design? And what would be the best operating conditions for such a competitive design? And I will show you that we use a lot of modeling to drive our decisions. And we also look at limiting efficiencies to understand the trends. So where should you actually go in order to maximize your performance, which can help you in minimizing costs? So I want to start to just tell you all the theoretical efficiency limits of photoelectrochemical approaches. You can use so-called equivalent circuit models to do that. There are a variety of people in the community who do these types of calculation. I show you a study here from Caltech, Kate Fontaine, which is showing you typical efficiency of a photoelectrochemical device as a function of the band gap of the semiconducting material. For an ideal situation here in blue, which would basically neglect any kind of overpotential you could have in your chemical reactions or any kind of transport limitations you can have in the semiconductor. And then she also introduced 2 more realistic cases. But effectively what you can see is the peak efficiencies are in the range of 30%, so certainly quite an interesting efficiency. So if you have worse catalysis or worse photoabsorber, of course, the peak efficiency comes down. So instead of 30, we would have maybe around 15, and you would also require different types of material to satisfy such a device. And you can even further push for higher efficiency by not using only 1 photoabsorber, but 2. Where you can see, if I have now 2 photoabsorbers with 2 different band gaps, you put them nicely in tandem, match their current, and you have effectively the possibility for a 40% efficiency device. And if you go a bit more realistic, it still seems that 16% is not away from anything achievable. Now, this 0D equivalent circuit model approaches are actually rather rapid. They're not computationally intensive. And so once we have, let's see, seen what possible materials could be important for the combination, what operating conditions could be important for the performance, we went ahead and used this physics-based model in economic and life cycle assessment in order to address what I just mentioned before, this more holistic idea that it also has to be cost competitive and sustainable. Promising device groups is what we try to define like this. And in order to do that, we basically made a high-level estimate what would be required for such a photoelectrochemical device, in fact, now system, in order for it to be workable. And so you would feed the system with information on the irradiation condition. You would feed the system with information on the materials and how you manufacture them. In order to get an idea on sustainability, you would feed it with cost parameters, and you would feed it with degradation information so that you can access information on operational time, cost, sustainability, and hydrogen production rate or efficiency. And so that's what we did. And we introduced two additional performance parameters where we said, okay, if your system has a concentrator, has a photoabsorber, it has a possible co-catalyst, you can actually play around with the ratio of these materials, effectively concentrating the irradiation if you change the area of solar collection to photoabsorber area, and effectively with a current dilution if you play around with the photoabsorber area and electrocatalysis area. And so if you do these types of calculations with this C, solar irradiation concentration factor, and with this F, this current dilution factor, and you pick a certain material combination, for example, as an extreme case here, 3,5 based materials, you get these types of solutions. So you have a range of solutions for an unconcentrated case, where the case F equals to 1, meaning photoabsorber area and electrocatalyst are the same in area, they're experiencing the same current density, is here, and the colorful solution space is spanned by all the possibilities with concentrated radiation. And so there you have again a subset of solutions where F is equals to 1. And so if you look at this space, you realize you have sort of a Pareto front, an optimal front of solutions in terms of efficiency and cost, and these are the only ones which we would consider. And then I can repeat the same game for a sort of another extreme case with rather abundant materials. And there, the solution space looks like this, generally lower efficiency, concentrated radiation, not that important. So the gray curve here is more interesting in terms of cost. And again, I can identify my Pareto front and only focus on these cases. And now I can sort of pick winners and losers by setting myself a target maybe on cost. And if you do that, you see that one interesting solution space seems to lie up here. These are cases with rather rare materials operating at very high current densities, though due to the fact that I use concentrated irradiation. So you could imagine this system to look something like this. In fact, later I will show you how we implemented it in detail, but it could consist of such a parabolic concentrator and a receiver in the focal spot, utilizing the high photon flux to convert this into fuel without actually going for high temperatures. So again, what we learned from here, concentrated irradiation can make these PEC devices interesting, competitive, and that mostly is a result of the higher current densities / power densities of these devices. And then also that rare materials can potentially still be relevant if the performance benefit is large enough at these high concentrations and you have reduced the mass of the material by a factor of 100 or even 1,000. And one last comment on this techno-economics, and then I go back to the performance, the technology development. We also try to think, if you have such a device and you potentially want to ensure long lifetimes, you might potentially replace some components of your device during a longer lifetime. And so we try to see what is the advantage if you replace, for example, the catalysis part or replace the photoabsorber part. You get an extra boost in production again, and you pay a little bit for the replacement. And we were able to identify for this particular case two minimums, so two cases where you have a small cost, which led us to conclude another thing, namely that you can follow two approaches in this case. You can either have a device which has components which are sort of a short lifetime. They are sort of disposable. You constantly replace them so that you can constantly increase your performance, but they're relatively cheap. And this is why, in the end, integrated over time, that makes sense. Or you have the other case where you have more long-term components and you try to keep them well operating without replacing them. And that would be the second optimum in this case. It's almost a little bit like with your car. You go in and get the engine fixed and you're not replacing the car all the time. Okay, so with this, we had an idea what we wanted to do. We wanted to use concentrated radiation. We wanted to use relatively high performance, potentially rare materials, and then started to think how to design such a system. And for this, advanced multi-dimensional and multi-physics simulations are necessary. And so the physics you have to solve are indicated here. You have to make sure that you account for electromagnetic wave propagation, so the absorption of radiation, semiconductor physics. So how are your electrons and holes which you generate, how are they actually separated and transported to the catalytically active interfaces? Then the charge transport in the electrodes and the electrolyte, which in our case is a solid electrolyte. Finally, the fluid flow, reactive fluid flow in porous structures, and the energy equation as well. Somewhat new. The details of the implementation you can find in the reference indicated here. But you can see that the energy equation looks at the first sight relatively simple. And then if you dive into the details, you see here basically a convection and conduction term, and you see a heat source term. And if you look into this heat source term, you see that you have a variety of contributions of heat sources coming from the different other physics. And this basically tells you that this is an extremely coupled problem. It's difficult to solve numerically, and this is also why practically it's actually difficult. So you have to somehow manage this coupled photo, charge, mass, and heat transport in order to ensure that your device will be operational and it will also be operating for a while. Because if you use hotspots, for example, it might be extremely difficult to ensure that you will continue with a good performance. So we went ahead, built it. And here you can see the actually built design, and then put into the focal spot of our high flux solar simulator. So the simulator is approximating concentrated radiation. Here you see the device from the back side. Photoactive area is 2 by 2 centimeters. And with this, we were able at about 474 times concentration to produce an output power in terms of hydrogen produced of about 30 watts at current densities that are in the order of magnitude of commercial electrolyzers. And we did this at a reasonable efficiency, 17%. Basically, I want to highlight this efficiency. It's not a peak efficiency that has been demonstrated, but for the high current density where you have to deal with so much larger losses than in low current density devices, it's actually it's actually quite an achievement. But let me convince you by just looking at all the different demonstrations that have been done in the field. You can see each data point is some university or research institute that has demonstrated hydrogen production. You can see that the colors on the shapes of these demonstration points are different, which are taking into account that different materials, different designs are used. So we're a little bit comparing apples and bananas, but nevertheless, it gives us an idea of the trends. Particularly, you can see here, everybody is converging or asymptotically reaching a limit. And this limit is in fact triple junction, a Schottky-Queisser limit at 1 son. And you can only push beyond this limit in terms of current density, which I show here on the y-axis, and efficiency if you use concentrated radiation. That's what we did. And here you can see our demo, which has 2 orders of magnitude larger current density than what typically is demonstrated. And this translates also into the power. So same demonstrations. Now I show in the x-axis the output power. And even though we have a 2 by 2 centimeter photoactive area, since we use concentrated radiation, this results in a larger power. So you don't achieve scaling by simply increasing the area. You can also achieve it by using concentrated radiation. And this gave us the motivation to scale. And here you can see a nice scaling picture, or let's say this is our solar parabolic concentrator, which we installed on campus. This activity has been ongoing now for almost 3 years. This parabolic concentrator has a diameter of 7 meters, and in the focal spot, we put our solar reactor. And so here you can see this integrated photoelectrochemical system. The photoactive area is now 12 by 12 square centimeter, and we're operating at about 900 concentration. I'll show you the exact data in just a second, but you can see that we have reached now kilowatt scale in terms of output power, and at the same time we're able to test the device in more realistic operating conditions. These are some details on the system. I will brush over these and directly show you results. So here we have 4 nice days of operation in August, and you can see that here is the DNI, upper left corner. You can see we have picked one day, which is not so nice, a lot of transients. We have one day where we have nice solar irradiation, pretty ideal, and then 2 days, which are sort of intermediate. You can see here on the right upper side, pressure in the system, particularly the blue one is the pressure in our storage tank, where you can see throughout the day we're filling the storage tank with hydrogen, and you can see this increasing the pressure, and then at some point we have used a little bit of the hydrogen, and this is where this drop comes. You can see on the lower right side production rates, hydrogen to oxygen. They are nicely have the nice 2-to-1 stoichiometry, but you can also see that the rates are correlated to the irradiation conditions. So if you have choppy irradiation, you have choppy production rates. Last thing are efficiencies. It's always a bit difficult to assess it, but if we look at the system level, solar to hydrogen efficiency, we have about 5% solar to hydrogen efficiency based on the standard Gibbs-free energy. If we look just at the device level, we have in fact 20% solar to hydrogen efficiency. So we lose a lot in the optics because the concentrator we have is not, let's say, very high performant one. And then if we also consider the excess heat which we produce at temperatures in the range of 70 degrees, and then we have truly a cogeneration system, and then we can put system efficiency producing hydrogen and heat to almost 45%. So you can see in the table here a summary a little bit. Particularly I want to point out the production rates. So the best day, almost 930 DNI, 7 hours of operation, and we're producing almost 0.5 kilogram of hydrogen, which is enough to drive your car for at least 100. So effectively, we have started from an idea through calculations, made a lab scale device, and then scaled this in a time of about 7 years. And right now we're trying to go to commercialization step. In fact, one of my collaborators trying to do this. He has founded this startup company where we try to make the next step from this single dish device to a multi dish device to actually produce hydrogen on an even larger scale. So this is the vision of the future. You can use this solar dish approach to produce hydrogen for industrial application. You could see this more as a chemical commodity. You can also think about this to be used in more domestic application, or to charge your car, fuel your car. We're excited to embark on this in the next. With this, I want to stop. I want to thank the team team who has done the work, particularly for the large-scale implementation. We have Isaac, Sorab, and Clemens. And then for the smaller lab-scale demo, Sylvain, Freddy, Alexandre, and also Sorab, who did the big part of the work. The funding has been coming mostly from Switzerland so far. Just now we received a little bit of funding from the European Commission, which will allow us to continue this journey. And with this, I want to stop. I thank you for your attention, and I will look forward to the Q&A after Joachim's.
Thank you very much, Sophia, for this very interesting presentation, and also for keep your presentation within the 20 minutes we allocated to your intervention. I think this was the best start for this technical morning session, but also gave us very good insight on the high relevance of public funded research, because I mean this is incredible, and also the fact that from a very technical ideas you can go to something that has a very strong economic value, not only maybe to drive the car, but also I'm thinking to very broad big application, for instance, to decarbonize the steel industry in Europe, which is something on the agenda, and also mentioned in the European Green Deal. So without further ado, I now leave the floor to Joachim to start presenting some of the findings of our study. Thank you, Joachim.
Yes, thank you, Felice. My name is Joachim Juhn. I'm from IMEC. Try to share my slides. Okay. Can you see my slides?
Yes, Joachim, you just have to go probably to full screen mode, because now we see the full PowerPoint.
Yeah, okay. That's all right.
Great.
Yeah, good. Okay. Good morning, everybody. Yeah, my name is Joachim Juhn. I'm from IMEC, and I will share with you our results on the electrochemical and chemical pathway of solar fuels. So there are a lot of roadmap exercises you can find on in the literature the last years concerning power to X. And so what I would like to show you here is actually on the left side, you see one of these examples of coming from the Sunrise Consortium, where very nicely they show the starting points of our research and where we want to go. So in this work, actually, I will concentrate on the energy technologies, electrolysis from renewable sources, and directly conversion from sunlight. At the end, we will make this roadmap exercise where you have on the y-axis technology readiness level, and on the x-axis a timeline, and you will have, we will work out stage gating in between to push the technology from a lower technology readiness level to a higher one. Methodology we are using for this is depicted in this slide. So we can distinguish actually 3 phases. The first one is the technology readiness level assessment, where we actually look at the state of the art and identify bottlenecks and critical points. Then we go to the stage gate process. So actually looking for a gap analysis and checking the technologies that are needed and the processes that are needed to go to a higher technology readiness level. And at the end, if you draw these findings over time, you come to a technological roadmap. So I will show you now first the technology identification, TRL assessments, and the bottleneck identification of the electrochemical and chemical pathways. So 3 technology routes are identified within these pathways, 2 direct ones and 1 indirect ones, also depicted on the graph on the right side. So the direct ones are the photoelectrochemical cell with electrode approach, then the photocatalysis with particle systems. And the indirect one is the combination of a photovoltaic cell and the electrochemical cell. You also see here that the technology readiness levels of the direct one are lower than the mature technologies of the indirect one. This is the same story, just a little bit more illustrated. So you see on the left side the combination of a photovoltaic device with an electrolyzer. So the voltage to split the water is coming directly from the photovoltaic cell. In the middle, the photoelectrochemical cell actually works with a photoelectrode, or maybe with two photoelectrodes. There are different flavors. We will go this in a little bit more detail in a few slides. And then you have at the end the particle system, which is actually a photocatalysis approach, where the photoexcitation, the charge separation, the diffusion, and the surface reaction happens in one particle, assisted by different co-catalysts, and they are responsible for the hydrogen production and for the oxygen production. So with this system, actually, I would like to start. So we did technology identification, and now I will show you the TRL assessment and the identification of the bottlenecks and the critical issues. So this chemical pathway, actually the photocatalysis using particulate or colloidal systems, we can distinguish three applications. One is the one-step photoexcitation, where you, as described before, have one particle with two different co-catalysts responsible for the hydrogen and the oxygen production. But this is very tricky because the separation of the production gases are difficult. So this is why more and more the development goes to the two-step photoexcitation systems, also called the Z schemes or the C schemes, where actually two particles are responsible for the two different processes, the hydrogen production and the oxygen production.
Sorry to interrupt you. There is a problem with visualizing the slides. Apparently, the margins, right and bottom part are out of the screen. So maybe you can go to not full screen mode and show just the PowerPoint so everyone can see the entire presentation. At any rate, I want to reassure you that the presentation will be shared with all participants after the meeting. So you will be able to analyze the slide with greater details after this session. Thank you, Joachim.
Okay, yeah, all right. And yeah, the two-step excitation systems actually distinguish between an aqueous redox mediator and the solid-state electron mediator. So the analysis of this system, the TRL analysis, actually gave that we looked at the compounds, the components, and we analyzed that the semiconductor particle has a technology readiness level of 2 to 3, so as the co-catalyst and the electrolyte. The challenges are manifold. I don't go in all the details of this technology, and you see there is, of course, a problem of corrosion, there is oxidation, there is phase composition, and many more. So let me go to the next technology that has been identified, which is actually the photoelectrochemical cell, which is in principle a very elegant way to use light for water splitting because it's a direct way, but here also the requirement list is long. So we have as scientific criteria on the material is that it needs a sufficient high band gap, the band edge is straddling, the redox potential of water, good transport properties, high catalytic activities. But this is not all, because at the end you need to upscale this to industrial level. And for the upscaling, there is also some other requirements needed, like stability in the electrolyte, abundancy, non-toxicity, and cheapness. So in order to mitigate these problems, there are actually, the scientists provide approaches, which is a combination of the photoelectrochemical cell and PV, which is depicted in this one. And this can be done with embedded solutions, like shown on the right side, where actually a triple junction of amorphous silicon is used to provide the necessary voltage, or like on the left side, you have two parallel connected silicon solar cells who provide the necessary voltage. There's actually a third possibility, which we just heard by Professor Hausener, and this is to concentrate the sunlight. That's of course also possible. So in order to give here a technology readiness level analysis, is actually the problem lies in the choose of the materials for the electrode and for the co-catalysis. Here the non-abundant materials are used, and as we heard before, if you only can concentrate the light high enough, then maybe there is a possible spot for application for even using novel materials in this. If this is not possible, then technology readiness level is between 3 and 4 for this application. The next step is actually going to the indirect systems, where we have the combination of photovoltaic cell and electrolyzers. Via electrolyzers, we are looking at the proton exchange membrane electrolyzer and the solid oxide electrolyzer. So this is the PEM electrolyzer. It's well-known technology. Technology readiness level is high. It's already 7 to 8, very close to industrial mass application, we can say. And you see on the left side a schematic drawing. So you have in the center, the heart of this electrolyzer is the so-called MEA, the membrane electrode assembly, where you have the membrane, the catalysts located, and this is encapsulated by flow rates. The analysis of the components gave that all the components are at relatively high level. The problems we see here is rather the use of the RAM materials. If you go to the solid oxide electrolysis cell, then this is actually the schematic you see on the left side. You have mainly ceramics as anode and cathode material, and also the electrolyte is mainly made from stabilized zirconia. So here the biggest problem due to the high temperature is actually the stability, the durability due to degradation, and a big problem in combination with renewable energy sources is actually the flexibility. And here we mean ramp-up times of the systems that operates at temperatures as high as 900 to 1200. The TRL analysis here gave that the electrodes, electrolyte, and the reactor design have technologies levels between 6. Now we are coming to the roadmap definition. This is actually the core of this presentation, because the TRL assessment has been done already earlier. So I want to go with you through this exercise in detail. So what I have shown you up to now is actually the assessment part. Now we will go to the stage gates and to the developing real. And at the end, the idea is to come out with a graph like it's depicted on the right hand side.
No, Kim, so, again, sorry for intervening. Can you remove the full screen mode, because especially for the roadmap, it's important to see the full graph and it's not visible to the participant. If you can go just to show the PowerPoint, yeah, it's better because, okay, this is the best way to show the slide. Yeah, perfect. Thank you.
I do it like this, okay?
Yeah, perfect.
Yeah, my problem is now I don't have the animation, but it's okay. We will go through it like this. So for the proton exchange membrane roadmap, we are started with a technology readiness level of 7. That means the system technology is demonstrated in the field, manufacturing approach is demonstrated, life cycle assessments, life cycle posting are evaluated. So what to do to come to the next level, and at the end to come to technology readiness level 9, which means technology is available for the market, full rate production readiness, and business plan is available. We think this can be done actually within the next 5 years for this technology. There are some problems to be solved. One of the problems to go to really large scale is still the platinum group metals for the catalysator, but this is now already, there's a lot of work to reduce it by using coatings on existing other metals. The substitution of the titanium feed plate is also important, and we are still working with an Nafion membrane, which is actually a development of the 70s. So here we see actually the chance for improve. And then there is actually a major question for this technology, and this is, I'm very interested how the community sees this. And this is, there are actually proposals to, in order to mitigate the novel metal use of electrodes, to go from a proton exchange membrane, to go from the acidic regime to alkaline regime. Because in the alkaline regime, you could use cheaper materials like nickel, for example, and would not need the novel materials. So is this actually the way how to fully commercialize this technology, to go to the hydroxyl exchange membrane instead of the proton exchange membrane? Or do you only mitigate the problem from the electrode to the membrane? So that's actually something which I think is very interesting and will be coming up the next 5 years. So further improvement is needed on the extended system lifetime and on the compact stack design. Okay, for the SOEC roadmap, the solid oxide electrode roadmap, we're starting with a technology readiness level of 6. So that means there are working prototypes in relevant environment have been shown. Here we think what is really important is to understand the already described very known, very complex processes that happen in these systems. So models are needed here, and physical understanding is required. The solid oxide membrane durability has to be improved, and of course the ramp-up time, which is now several hours. The big strength of this technology is that it can work with co-electrolysis. So that means CO2 can be used in combination with water and can provide syngas, carbon monoxide, and hydrogen. So this strength has to be further developed because this can be really a differentiator in the market. And if this can be coupled with a Fischer-Tropsch process, and this can be included in this system, then the way is open to go to even more complex hydrocarbons, like synthetic diesel or kerosene. For that, the stability and the ramp-up time has to be improved. And to go to full commercialization, and we think this can be possible within now and 10 years, the key is that these systems can be connected to renewables. And this can be done in 2 ways. Either the ramp-up time is further reduced in the minute range or even more, or, because this is maybe tricky due to the temperature constraints, it can be run together with batteries in order to provide continuous operation. And we think important here is also the production of more complex hydrocarbons in this system. So now, I go to the next slide, which is actually the analysis of the photoelectrochemical system. And you see here, because we're starting as a lower technology readiness level, actually the prediction until 2050 is very tricky, because this is more crystal ball reading. So the timing when this technology really can go into production, I think we have an arrow here of at least 10 years. So we can also formulate it positive. There are different scenarios for the timing. What nevertheless remains is the challenges that has to be overcome to come from one technology readiness level to the other. And I will go with you through them from the bottom to the top. We think the first thing which has to be studied is actually to avoid these high performance materials, which are normally very expensive, or at least to minimize the use. One way out would be to go to relative cheap transistor metal oxides. The stabilizing of the semiconductor catalyst system in liquid is also a problem that has to be overcome. And also here, again, physical understanding is required by modeling the novel materials in these devices. The next step will be then to go to for the upscaling. Always the requirements are the same. Novel metals are a problem, rare materials are a problem. So either limit the use or do not use them. We also here for these technologies need scalable coating methods, because we have now in the moment lab methods what we are using, but they have to be upscaled. Like Sophie Hausner said, we are targeting gigawatt scale. Then we need also a device platform where actually the testing can be provided. So we don't want to compare apples with oranges. We want to really see how different materials working on the same device. In order to go further, I think, or we think, that the way to bring this system to commercialization is actually the way, as it has been proposed in the talk before by Professor Hausner, is the combination of PV or concentrator solar with this system. So hybrids will need to be used to go there, either with high efficient tandem PV cells or with concentrated cells, in order to bring up the efficiency. Then on the processing side, upscaling to roll-to-roll methods are required. And it would be also very nice if co-electrolysis could be developed with this system as well. And at the end, we think that these systems will be mainly used for standalone applications in households or in local energy communities. I go to the next slide, which is actually the photocatalytic particle system, where the starting technology readiness level is even lower due to our understanding. So the requirements for the stage gate are higher, and here I also going from down to up. We think to go to the next technology readiness level, what is required here is to understand and to develop a cathode for dye-sensitive photocatalysis, the modeling, again, physical understanding of the very complex light-driven electron transfer processes are required, and the gas separation membranes for two back systems, the two-step photoexcitation, need to be developed as well in order to separate the gases. We think in 5 to 6 years from now, the natural photosynthesis can be mimicked in the lab. And the self-assembled surface layers will play an important role for these kind of systems, and they will be based on nanoparticles. The product separation, the hydrogen and the oxygen, for the single bag system will be developed then or need to be developed. Because of oxidation and degradation of the catalyst is reported a lot, self-prepared surface layers based on nanoparticles need to be in place in order to repair the systems at the spot where degradation takes part. The processes has been synchronized. There has to be, they are in the moment not in the same range, so that means photon excitation, diffusion to the surface, the catalyst reactions have different time scales, and they have to be synchronized. The ionic charge carriers mediators need to be developed. And then we are at the upscaling. When we are at technology readiness level 6, we have to think about upscaling. Then the same requirements kicks in that we already had before. Reduce or avoid novel materials, scale the coating methods or the processes, and provide a device platform test. Then the upscaling to roll is important to be developed, and co-electrolysis would be also help a lot. So direct air capture in combination with these systems will be very useful. So this is at the end. You see that until 2050, except that we are in a very optimistic scenario, we don't think that this kind of system will make it to industrial application, but we can come very close. So this brings me to the end of my presentation. Sorry for the hassle with the slides, and yeah, I'm very happy and waiting for the Q&A session. And I think, please correct me, CEPS organizers, if we have a poll.
Yes. Should I start it now?
Yes, you can start.
Okay.
Yeah. I stopped sharing my slides.
Okay, Joachim, so the poll is not part of the Q&A, is to conclude the presentation of Joachim. So we allow you for a little bit of time to consider the question and answer. And maybe Joachim can comment upon the result. Maybe, you know, while waiting for participants to answer the poll questions, we could start the Q&A session in parallel. I want to remind to all the participants that they can write down question in the Q&A box, and we will take care of answering the question in this moment. As I don't see any question written there, I would start with some curiosities that I have. I'm not a technical person, I'm an economist, so I'm still, you know, very interested in the economic and policy aspects of your presentation. So the first question I have is for Sophia. I understood that policy support in terms of public funding has been essential for your program and maybe still essential for further development. But on top of public funding, what are, in your opinion, the external factors, those maybe on which policy can intervene, that would support the future development of this technology?
Yeah, this is a great question, Felice. So what we observe now when we think about going larger in scale, making demonstrations that can reasonably interact with partners, it's very capital intensive endeavor. And so you have to think where this money comes from. You can either partner up with big players, or if you want to keep sort of independent, this route is very difficult. So I see this value of that. I really see this here, mostly because the investment that is needed to do simple demonstration where we cannot yet guarantee, you know, a product with certain efficiency and warranty and whatnot, where we still need to play around and learn about the system and record performance. And so to us, this is one big component. So foundations can maybe jump in, industries, but industries are sometimes almost shameless in trying to get from you everything that has publicly funded for pennies, where I have my big concerns also. That would not be a sustainable business way forward. Yeah, and then the question is whether there are larger sort of grants, maybe from the European Commission or beyond, for such larger demonstrations. So to me, these are some questions and points of discussion maybe also.
Maybe the Innovation Fund could be one of those that could bridge the gap and save you from the valley of debt. But I understand that the European Union can play a very crucial role in this, more than national funding. So, I mean, I think that the DG Research and Innovation is also the right place to discuss this, because they are working a lot on sequencing and blending public funding to ensure that, you know, you can go from very low TRL to commercialization. Mm-hmm. So this is key. Joachim, I would also include you in the conversation because, you know, the poll is still ongoing, so I might ask you something. You have presented a number of technologies. At least I see at least 4 family of technologies in your presentation. But I mean, I have again a question as an economist, not as a technical guy. So if you were asked to invest all what you have on only one of the technologies you have presented, which one would you select and why?
Yeah, if I have to invest all my money, I first have to ask my wife. So that's, thanks a lot, Felicia, for this question. No, it's very relevant. I have to say that yeah, of course, the technologies which have a high technology readiness level are in the moment the most predictable. So we can see that here within the next 5 to 10 years will really something happen. And I also see that there is a huge industrial jump on these kind of technologies because they see that this is the way to go. So I think the proton exchange membrane electrolyzers or the solid oxide electrolyzers, this will be the technologies which will come first. And yeah, in which flavor they will come with co-electrolysis or as an alkaline exchange membrane. These are details, but these electrolyzers will come and they will they have to provide gigawatt scale production. That's what is important.
Thank you, Joachim. I have another question, and then maybe we can move to conclude the Q&A because I still don't see any question from the participants, so I keep the discussion based on my curiosity. So the European Commission, especially the new Commission, the von der Leyen Commission, but also the Commissioner Breton, is placing a large emphasis on EU sovereignty and global leadership in key technologies.
Yes.
So we want to be global leaders. So yes. I would like to ask you, but maybe also Sophia can intervene in this based on her experience. Which of the technologies that you have presented is the one where the EU has higher chances to lead on a global scale, so to become, you know, a global leader?
Mm-hmm. Mm-hmm. Maybe I can answer first, Sophia, if that's okay for you. Yeah. Okay. So yes, that's a very good question, Felicia. Thanks a lot for that, because the answer I gave just before, using these solid oxide electrolytes and the proton exchange membrane technologies, they of course have their strengths when they are connected to very cheap renewables. So that means the production of hydrogen must not per se be done in Europe, but maybe somewhere where we have access to very cheap renewables. And I think this is also why, and maybe the colleagues from the Commission can also say something to that, there is a strong collaboration with the Maghreb countries, North Africa needed, because there the production of very cheap photovoltaics, for example, can be guaranteed, and with that also a very low hydrogen price. But of course we need to be sure as Europe that we have access to this hydrogen produced in these countries.
Thank you, Joachim. Sophia, do you have any view on this global leadership of the EU or Europe on these technologies?
Yeah, so maybe just 2 points. I mean, Germany and Spain have been big leaders on solar, CSP, concentrated solar power, and Germany a lot with EV. And I think piggybacking on this is definitely possible with some of these technologies. And so I see a great potential there, in fact, for a leadership of Europe and sort of building on the already started leadership in these areas.
Mm-hmm.
Thank you. Sophia, I see that there is a question for you in the Q&A box. I ask any attendees to write their question, not in the chat, because we cannot take care of the question in the chat, are very difficult to read. So from Mr. or Miss Bardizza from the European Commission JRC. Sophia, do you want to answer this question live?
Yes, sure. So the question is about the hydrogen use for vehicles first. So I kind of want to take my opinion out a little bit. I would say if there are companies who are happy to develop hydrogen cars, which they are, we gladly, let's say, provide fuel for these cars because we somehow have to have a renewable hydrogen production chain that is leading up to this. Otherwise, yeah, you have to ask yourself where the hydrogen comes from. This also requires, however, that you have the infrastructure adapted, right? You might not always be able to produce the hydrogen on site, so you need pipelines and whatnot, distribution networks. And so this is where, if we talk about hydrogen as a fuel for car, I think it goes beyond just being interesting from an efficiency point of view for the car itself, but also how will you actually make this whole economy around it work. And the second part of the question is then alternatives, whether we would go, as far as I understand, so could we also do methane-based products? So to me, this would be such a hybrid approach, right? Because methane is a fossil fuel. And so I have maybe of the extreme position that in the future we should be completely independent of fossil fuels. So the midterm sort of goal that such hybrid approaches could be interesting, but in the longer term, I think we should really go away from these fossil fuel resources. I hope that answered the question.
There is also another question for you, Sofia, from Antonio Ottavio Patrocinio from the Universidade Federal de Uberlândia. Could you provide more details about the converting device components you have used in the large-scale demonstration?
Yeah. So, I mean, here I want to maybe first start by giving a comment on scaling of photoelectrochemical devices. So there is a notion maybe around this community that scaling simply means you're increasing the area of your photoabsorber, which is partially true, but only partially, because again, as I tried to show in my presentation, scaling can also be achieved by using intermittent sort of under intermediate optics, and then you can use a smaller area of photoabsorbers while still making large power. So scaling doesn't necessarily just result in large photoabsorber areas. Yes, the collector area still has to be large, and this is what we do with them. Now, details on the components. We use 3-5 materials for the photoabsorber, so it's a highly efficient triple junction PV, in fact, which is in direct contact and communication with the reactant and with the electrochemical component, which is a solid electrolyte based, sort of PEM-based electrolyzer. But the innovation is, in fact, in the integration of the two. So, yeah, I think that's what I can say there.
Thank you, Sofia. I see another question for you. So you're really the celebrity of this Q&A. So the question is from Mukund Bhagwat from the European Copper Institute. So they pay attention on cost of these technologies. So will we know the estimated cost of 1 kilogram of hydrogen produced from now until 2050 based on the proposed technologies? And which specific research areas need to be further investigated?
Yeah. I mean, so will we know? I don't think we necessarily know. You know, you can sort of try to think about learning curves and whatnot to try to estimate from a starting point where you expect to be going in terms of cost by maybe 2050. But I think this is maybe a bit beyond what we do. I mean, in the end, we still try to develop technology, and the cost aspect we try to give to the companies. And so that's the approach I would take for the estimation of cost in a 2050 horizon. And then the follow, or the second part of the question is, where basically do we see where we have the biggest handle maybe on these costs? And here I also cannot yet really comment on, because the system we have built here, we have a first idea what the different components cost, and post-processing of the product is actually something unexpectedly important and costly. But at the same time, this is nowhere near a solution which you really would use on the larger scale. We buy individual components, and so it's very difficult to estimate what that would mean for a more scalable system. So I would say balance of system is important for the cost.
Hi, Felice, Felice Sophia. This is Nick Merriman at Ernst & Young, and essentially, apologies for jumping in. I know we're a little bit overdue for a break, but I just wanted to let Mukund know that essentially this is a great question, and we're quite excited actually to give you maybe just an overview of. We're essentially going to be answering that question later today in the afternoon session, where we will be indeed discussing these topics. You know, there's cost evolution of hydrogen. So, you know, please stay tuned for that. Indeed, applying the learning curves and concepts that Sophia has brought up. So, yeah, I just wanted to let you know, and maybe let the entire audience know as well that we will be, you know, providing some of our estimates for these, you know, these forecasts in the afternoon session.
Thank you, Nick, for intervening. So before taking the next question, and then I will leave you for the break, we are a bit over time because we started a bit later. Joachim, do you want to comment upon the result of the poll, please?
Where do I see them, Felice?
You should see them on the screen.
On the screen, yes. So I can read them, and maybe you can comment upon them. I'm not an expert. So basically, the first question is, do you think PEM electrolyzer should remain working in the acid regime or mitigate to alkaline exchange membrane electrolyzer? And yes, the most answered question is the third option. So mitigating to alkaline may solve the PGM catalyst problem, but the membrane challenges remain or even increase. So what is your note on this?
Yeah, I think that's, yeah, that also that follows exactly our thoughts. Can I ask how many percent?
50% there, and 1/3 for the second option. So mitigating to alkaline is the right way to go. This simplify the catalyst choice.
Yes, okay. Yes, I can comment to that. Yeah, thanks a lot. First of all, for this answer, I think it follows our ideas that you transfer the problem from the electrolyte to the membrane, but of course the membrane is then a technological problem, while the electrode problem, maybe using novel materials, is not so easy to be solved. So it's just a mitigation which maybe can accelerate the industrial use.
So I go to the second question, PEC electrode systems. Which critical issue, bottleneck, needs to be solved first to accelerate the development of PEC? So 50% of the respondents have selected the semiconductor catalyst stability over 1 year. 1/3 went for materials for upscaling roll to roll. So again, Joachim, what is your view?
Yeah. Thanks again for participating here. Also this, I think if you look at the priority list in the road mapping, is also what we thought. So this confirms actually our idea on this topic. The upscaling is something which has to be tackled later. Of course, has to be kept in mind by developing materials. But the first problem is indeed the semiconductor catalyst interface in the loop. Yeah, I fully agree. And that's a good outcome.
Thank you, Joachim. I leave room for answering the last question we have in the Q&A box. So I don't know if you or Sophia want to take it, and then we go to the break. So who is volunteering for this?
I can maybe give it a start, and then I'm sure Joachim will add to it. So in fact, our depurification is not based on heat. So we're not doing a sort of a distillation process for this. So in this sense, it's not really competing at this point. In fact, whoopie possibly is suggested here, but we have not considered it. Instead, we're using relatively pure drinking water here in Switzerland that comes directly from the mountains. And so the purification is, I would say, less severe than maybe in other places. So it's definitely a great question. how pure does the water have to be, how much we have to spend on this energetically and cost-wise, and how potentially this can be even integrated in the full device. So to me, open question, great question actually.
Yes. Yeah, I can only agree with what has been said by Sophia. I think the question is very relevant, and I think between the lines, I also, of course, see the story of the using salt water, because this is the saltwater electrolysis. I think is a very interesting one, because obviously we have more salt water than sweet water on Earth, and not everywhere, Sophia, is the quality of the water as good as in Switzerland. that's I think clear. So the question is very relevant and very good. And yeah, I agree. You know, with the high temperature applications, of course, steam can be an option and is maybe interesting to look at it. But yeah, purification in the moment is not looked at. Yeah, I agree.
Thank you, Joachim. Thank you, Sophia, for participating in this Q&A session, which I found very interesting. We are running a bit late, 10 minutes late. So I'm now starting the break. I invite all the attendees and panelists to stay connected. You can just mute yourself and turn off your video. I would ask you to come back and you know, be ready to participate again at 22 noon. So we are starting a 13 minutes break. So see you soon for the second part of the morning session. Thank you. So we are almost ready to start the second part of this morning session. I would ask Andrea and Alessandro to get ready for their presentation. Now our colleagues from RINA will present the thermochemical and biochemical pathways. Of course, I mean, they're part of the study team, so their presentation will show the findings of the study. Alessandro, Andrea, thank you for connecting. I now leave you the floor, and then we will have a Q&A right after your presentation. Same rule as before. Attendees can write down the question in the Q&A box. They can also do it while you are presenting. We will take all the questions right after your presentations. So thank you again, and good luck.
Thank you, Felice. I will start for my part. I'm going to share the screen, and then we'll get ready. I guess you are all seeing the slides. And my name is Alessandro Venturino. I am a mechanical engineer at RINA Consulting. I will present to you the results of our analysis under the thermochemical pathway tier, whereas Andrea, soon after my presentation, will introduce the second half, the biochemical pathway. Well, just an introduction on which is our focus. So what do we select under the thermochemical pathway? After a screening of available technologies and solutions, we got to the conclusion that we investigate on the hydrogen recovery after a chemical reaction, hydrogen production, I want to say, and water splitting, oxygen splitting, in a reaction which is based on solar captation. Here on the left, you can see two possible configurations of a reactor based on radiation from the sun, caught by heliostats or a parabolic concentrator, sending the radiation onto a receiver and then connecting that to a reactor. On the right side, we can see a schematic representation of this two-step reaction, which has from solar energy, then the reduction of a metal oxide, a generic metal oxide, with the release of oxygen, and then in the reactor there is the water splitting with the reduced oxide, which is oxidized and combined with the release of hydrogen. Then hydrogen can be used and delivered to further utilizations like storage and transmission for the use into alternative fuels, for example, which is an interesting field. We will see in the SWOT analysis which are the main interesting points of this reactor. I can quote now the fact that it's a reversible reaction. In the technology identification, here are two examples. For example, on the left, there is the two-step cycle, which is really similar to the previous scheme, in which we obtain hydrogen and water by concentrating the sunlight onto a receiver. We can see from this schematic that the thermochemical cycle requires very high temperatures, which is one of the most challenging points of our topic. On the right, the second picture shows an hybrid system. In this case, there is a combination of the concentration of sunlight with the external support, let me say, of other energy, so electricity. Here we combine electrolysis with the thermochemical reaction, and we finally obtain hydrogen and water again. I have underlined in this slide that the TRL of this solution is 5 to 7. This means that there are solutions tested into laboratory, but we still haven't got to the conclusion of the path, and so we don't have the commercial use of this system. The challenges that we identified during our analysis are related to efficiency and durability, decomposition, corrosion of the materials, and the design of the reactor. Here we can say a few words more on the TRL definition. Let's consider that our system, solar captation and reactor, is composed of parts which have a different degree of maturity. I want to say with this that the mirrors for the captation of the solar radiation are a very mature technology, because they are used and widely applied for the conventional solar system, the huge fields of parabolic concentrators. So their TRL is high, and we can assign a score 9 to that. The parts where we have to investigate and work more on the TRL is related to the reactor and its materials, the absorber, the redox materials. There we have assigned a 5 to 7 score, because the checkpoint still to be achieved is that the prototype is tested in the intended environment and not just in laboratories. We have made a patent analysis, and here are shown some exemplary pictures of that, to see that something is moving in the research for them, especially in the Far East, where there are also incentives and subsidies to study these kinds of applications. And there is a quite encouraging number of patents delivered in the latest years. And what is the step that we have identified under investigation? We see that as for solar radiation captation system, as I said, we are just working with the scientific world are just working on the optimization of the system, because that's a mature technology, as we said. On reactor design and geometry, electrodes, electrolyte structure, redox material, the work is carried out to define the overall structure of the system, to make the right tuning of that, and so to get to the perfection of that. Whereas for hydrogen recovery, it's a downstream process, which is fully another word. We mean with this that it's again almost mature technology, which is under investigation for other applications also, so all the world of alternative fuels and so on. So with this, we want to stress on the importance that the current analysis was based on the reaction and on the reactor side, and not on hydrogen recovery, transmission, storage, and so on, as well as on the solar radiation, who are, as we said, mature and well designed and well advanced. Let's move to the SWOT analysis. What do we see as strengths for this application? Theoretically, there is high efficiency in the process, and the process is reversible. almost reversible for most of its components. We can exploit, as we said, the high TRL already available for the mirrors. And there is, let me say into brackets, low energy input needed, because the energy input needed is very high in terms of high temperatures to be achieved, to be guaranteed to the system to work, but low in terms of free availability of this energy if exploited through the solar source. However, if we move to an hybrid system, of course, the energy input from the external can be also not remarkable. So we have to keep into account which system is chosen. And an important point to underline is the output fuel as a global warming potential equal to 0. In the weaknesses, we find that the durability of materials is still to be increased, as well as the design of the reactors shall be improved to face the high temperatures in the game, as well as the fuel, the hydrogen storage has issues with the high pressures to be kept. Another weakness is the fact that the startup time for the reactor is quite high, and this must be combined with the availability of sun, so there is not an easy warm-up period, and the operation and maintenance costs for the reactors are quite high. On the other side, opportunities, there is high purity oxygen as a byproduct that can be considered, as well as the technologies that are under investigation as emerging now show a good durability. So there is a good reply to the weakness identified before. There are also lots of R&D projects related to the concentrated solar power sector that can support the good captation of the solar radiation. Among the threats, there is a high competition with other alternative fuels and other pathways. There is a high thermal energy demand, and together with this, there are a lot of heat losses that cannot be recovered at high rates. The main threat I want to underline here also is the need to hurry up in the scale up of the solution, which is still at the laboratory stage, and we need to move to a real environment. Last but not least, another point that shall also be addressed in the economic side of the analysis, maybe this afternoon, is the competition with the cost of conventional fuels. With this, I want to say that since the fossil fuels cost is still low due to the fluctuation of the market, in this period, the cost of a kilowatt hour produced through this path is not that competitive when compared to a fossil fuel based one, and this poses a serious limitation to this. Let's move to the roadmap and its schematization. Well, where are we now? We are, we said, TRL 527, so we have a working prototype in a relevant environment. The timeline that we believe realistic at the moment says that in a 5-year time span, we need to identify the most suitable materials for durability and efficiency and move to a pilot case of a significant power, 250, 300 kilowatt thermal, and with a good efficiency, up to 15%. Then in another 5-year time span, we must demonstrate the system, the technology in the field. So by reducing the operating temperatures, increasing more the efficiency, and get to a reduction of the production costs for hydrogen. Finally, by 2035, we assume and hope that we can have the first of a kind commercial system, and acting on minor changes for the optimization of the operational conditions under the variables that can be, we have the full technology deployed and proved in its final form with commercial deployment by 2015. This is the timeline that we have assessed and we believe reliable under the present conditions and the present trends. With this, I have moved to the conclusion of this quick overview, and I want to thank you and wait for your possible questions for the forthcoming session. I leave.
Thank you, Alessandro. Thank you very much. Now, Andrea, it's your round. So you have to unmute yourself.
Here we are. Can you see my slides?
Not yet. Perfect.
Okay, thank you very much. And good morning to everybody. And thank you for attending these events. I'm Andrea Roncini from RINA Consulting. I'm a chemical engineer, and I'm going to present the main outcomes of the study focusing on the biochemical pathways. In the present study, two main systems have been analyzed within the biochemical pathway. The first one dealing with the biohybrid system, and sometimes in the literature it's also called as a bionic leaf. This mainly consists in the coupling of the photoelectrochemical step with the biocatalytic step, where engineering bacteria or enzymes are able to convert reducing equivalents provided by the photoelectrochemical cells into targeted chemicals, in our case, fuels, solar fuels. And the other systems analyzed is a microalgae based one. Regarding the biohybrid system, in the figure is report just one of the potential configuration of the system, consisting in this case in the water splitting and the photoelectrochemical water splitting, and with the production of hydrogen to be then converted by an engineering bacteria into, in this case, isopropanol or other kinds of alcohol or other kinds of fuels. So the overall configuration consists in two parts, as we say, in which the light is harvested and converted into reducing equivalent like hydrogen, like electrons, and then these reducing equivalent are provided to the biocatalytic steps to be converted into fuels. The main components of the system consist in the light absorber, in the cathodes, in the electrode, and then the cathodes, and also in the engineering bacteria parts. The overall system actually is performed at, let's say, at TRL between 2 to 3, which means that all the components, for all the components, the technological concept is defined. These are reports another example of biohybrid system targeting the production of ammonia through different bacteria. So the different fuels can be targeted actually according to the bacteria used and the engineering pathway used. These are the main technological challenges related to the system. They're related to the efficiency of the system, so the solar to fuel conversion, let's say, related to the reactor design and configuration, also focusing on the comprehension and the knowledge about the bacterial electrode interface, and also for the transfer mechanism of the reducing equivalents from the photoelectrochemical parts to the biocatalytic parts of the cells, and also other challenges more related to the metabolic pathway within the engineering bacteria, so the bacteria growth, the fermentation yields, and then the downstream processes to recover the produced fuel from the cells. These are the main points carried out within the SWOT analysis. There are some strengths related to the system, in which, as we say, different products can be targeted depending on the microbial strain used. The system is based also on the conversion of CO2. So also CO2 from other processes can be used in order also to lower GHG emissions, greenhouse gases emissions from other processes, for example. And they are also the system able to operate under mills operating conditions. There are also some challenges, some weaknesses related to the process in terms of durability of materials, solar to fuel efficiency, the transfer mechanism, as we said, and also the more challenges related to the biocatalytic part in terms of yields, fermentation yields, in terms of grow rate, in terms of genetic modification of the strains and the enzymes in order to reach the targeted yields and efficiency. There are also external opportunity mainly related to the trend in the market for the products. So there are increasing demand for sustainable fuels, for sustainable bio-based products, and there is increasing progress in terms of research for genetic engineering, synthetic biology, and also artificial photosynthesis, and also potential incentives for CO2 utilization or market deployment for solar fuel could boost further the development of the present technologies. There are also some threats related to especially related to the low or fluctuating oil and carbon price, and also the potential shortage in critical raw materials, especially for the light harvesting and the light absorbing phase. These are the overall schematic configuration, the roadmap between the current, in order to start for the current TRL and to reach the full-scale configuration of the biohybrid system. Many actions are required in order to, as we said, increase, for example, like light absorption efficiency, also to increase the durability of the material, and also investigating some for less critical material in order to prevent a potential shortage in the supply of this material. And also some actions are needed to increase the overall efficiency on the metabolic part of the system. This will allow to reach before a pilot scale and then a demo scale production of this biohybrid system in order to reach also solar fuel conversion between 8 to 10 to be quite competitive in the market. And then finally, the overall sustainability of the system in terms of also the CO2 supplies and the overall, let's say, environmental, social also, but also economic sustainability of the system have to be optimized. These are regarding microalgae system. These are the second system analyzed. Microalgae are phototropic microorganisms able to exploit solar light as main energy source in order to use CO2 and also an organic nutrient to produce a different kind of products and different metabolites to be used as starting and intermediate compounds in order to produce a plethora of different bio-based products. In our case, the target obviously has been put on the fuels, and so several very different plethora of biofuels can be targeted. This is the overall scheme of an example of value chain of the microalgae, consisting of microculture cultivation in open ponds or closed photobioreactor, the harvesting and the watering phase, the pretreatment of the recovered dried algae in order to extract the metabolites, the targeted metabolites, for example, carbohydrates toward bioethanol production or lipids toward biodiesel, but also the system is able also to exploit any residual streams, potentially any residual streams, in order to produce other kinds of biofuels or products like biogas, biomethane, to be also used in a circular way within the system. These are the list of the components of the system, mainly related to the cultivation phase, the harvesting phase, and the downstream processes. As we say, you can see that there are many components and many TRL involved, ranging from 5 to 6 to 7 to 8 for the most advanced components. And there are many technological challenges still related to the processes, related to the light penetration, distribution, the cultivation system, the mixing in order to provide effective distribution of light, nutrients, air, and CO2 within the microagriculture. There are other challenges related to the harvesting, the watering, the yields, in the saccharification, fermentation step, for example, for the bioethanol production, and also some issues related to the effectiveness of the downstream processes. In this slide, I will also report some two graphs regarding the patent trend. These patents are related to the biofuel production from microalgae. As we can see, there was an increasing trend, at least up to 2015, and then the trend started to decrease. Mainly, this trend can be mainly related to the decrease in the oil price, and this hypothesis can also be confirmed by the fact that the patents generally related to the microalgae do not show this increase and decreasing trend, but almost a stable or even bit increasing trend. And the main countries involved as assignings, to which the assignings belong to, are China, Republic of Korea, and the United States. Many strands are related to the microalgae chain. For example, the fact that microalgae can be cultivated in non-arable land or even in marginal lands, so potentially no direct competition with food chain is foreseen. The algae are able to use, even if some challenges are also involved in this phase, to use CO2 and nutrient-rich CO2 for other processing, for example, flue gases or nutrient-rich wastewater to grow. There is opportunity to increase, to perform a co-production of different products other than fuels, but also high added value compounds. And algae are also able to achieve theoretical light to biomass conversion up to 4% compared to the 1% that can be achieved by terrestrial plants. In terms of weaknesses, there are still some issues related to the cost, the cultivation, in the harvesting, in the water, nutrients, and energy required for the performance system, and also related to some logistics about the CO2 supplied, because if you, for example, we foresee to use the CO2 from flue gas, we need to be next to the CO2 source. There are also some opportunities related to the demand for biofuels, for sustainable fuels, the potential use for water entailing less competitive use like seawater, brackish water, or wastewater, and also again the opportunity to use CO2 and nutrient for other source, which can also be related to some threats regarding especially for the oil and carbon price and the alternative use for nutrients for wastewater. This is a schematization of the technological roadmap, starting from the current situation and towards the final large-scale biorefinery, algal biorefinery. Several actions are needed to increase both the light distribution and lower the photon emission risks, to increase the algal growth rate, to increase the fermentation yields, especially in the bioethanol production, to increase the efficiency of the system, and also entailing a very circular approach in order to use many, or at least almost all the residual streams carried out in producing the process in order to valorize them in terms of both for energy requirement, to provide the energy requirement to the system and lower the energy resource consumption, external resource consumption, in order to reach, let's say, a full co-production biofuel and added value compound in algal biorefinery, a solar to fuel conversion between 5 to 10%, and by targeting in the next maybe 20, 30, 25 years, a large-scale algal biorefining targeting also, let's say, at zero waste in order to increase the overall sustainability of the system from the economic, environmental, and social point of view. And thank you very much for your attention.
Andrea, thank you. So, the usual reminder, all the attendees can write their question in the Q&A box, and we'll be very happy to answer those questions now. As so far, I do not see any question written down. Again, I have, you know, my curiosity as an economist, so I found very interesting the slides you showed on the patents. It seems that, you know, most of them are in China, Republic of Korea, and United States. So again, I go back to the same topic that I discussed in the first Q&A. So Europe is aiming to this need for sovereignty and the global leadership. So did you take this into account when doing your analysis? And ask this both to Andrea and to Alessandro. And based on the patent trend you have presented, does Europe still have any chance to be a global leader in the thermochemical and biochemical pathway?
I can start answer for the biochemical parts. Actually, yes. Actually, the patent trend will also be considered that may include a plethora of different technologies and also different, let's say, parts of the system, because many patents could be related, and we analyze also patent related to the cultivation phase. It entails most of the patents, and others can be related to the genetic modification of the algae strains to increase the productivities, for example. So there are many aspects of the overall value chain of microalgae that can be, let's say, targeting for research and also for patent application. Regarding your question about Europe, yes, I think Europe has any potential on this field as for the overall bio-based sector, bioeconomy, and maybe up to now, the most of the focus, and especially also for microalgae, have been focused on the production or other valuable compounds like food ingredients, nutraceuticals, pharma, and so not specifically for biofuels, for example. This is good. This is why maybe in the, for example, in patent analysis, Europe can be a step behind, let's say, for other countries, but a lot of marginal lands, for example, can be used. Solar radiation also can be an issue because, for example, some area in other continents can be, say, more irradiated by solar, but again, there are plenty of also infrastructure in Europe that can boost the further development of these value chains.
Alessandro, what about the thermochemical pathway? Can we lead in that?
Actually, in the thermochemical pathway, we are a step behind other countries, I must be honest, but because I was saying also in the presentation that Far East countries and also the United States are investing more in these kinds of research, whereas in Europe, we are mostly focusing on the other sides of our process. So in the CSP, concentrating solar power, so the captation side, or in the distribution and transmission and storage for hydrogen. In the core part of the process, we don't have the full lead.
Okay. Another question I have, because we still have maybe a couple of minutes, and then there are no questions from the attendees. in this kind of process, to make sure that the roadmap develop in the way you have foreseen, there are many internal, but even more importantly, external factors that you should account for. So my question would be more about what are the external factors that can impact on the roadmap, and to what extent you believe that some of these external factors can be improved by policy decisions at the EU level.
I can start answering for the biochemical parts. Yes, indeed, we need to consider, for example, as we also see for the patent trend regarding the biofuels, the oil fluctuating and the lower oil price can also obviously impact on the research for alternative fuels, because still entail higher cost. So with less and lower oil price, the competitiveness of these by new alternative fuels, especially for the bio parts, let's say the most the ones require the further developments can be hindered by this market situation. And regarding the political parts, obviously also the carbon price in terms of CO2 emission and the boosted the incentive to utilize CO2, to capture CO2 and utilize it in order to reduce the greenhouse gases emission, and also to valorize this flue gas reaching CO2 can obviously be impact and affect the overall development of this technology, because there are related many potential to recover CO2, to convert it into higher bio compounds, but again, they need incentive to industry, especially to boost in the industrial investment on this field. It requires some, let's say, external boost to this field.
Alessandro, anything to add?
Yeah, if I can complement Andrea's view, which is perfect also for me. The point to stress maybe is to incentivize the greenhouse gas emission reduction in some way, to exploit the benefits from these new technologies that has, as we said, no global warming potential at all, or very low compared to fossil fuels. And so the boost against the competition with the cost of conventional fuels can come from some political instructions, integration schemes, and similar.
Okay, thank you. There are no questions, so I just probably want to recap one of the main message of the day in terms of economic impacts, and more will be discussed this afternoon. It seems that all the technologies you have presented for the time being and in the coming future will be more costly than conventional fuel. So from my understanding, it's key that the policy framework at the EU level will accompany the transition by make this investment more competitive. We are all aware that the EU has the EU ETS system for carbon pricing, but I also am aware that the Commission is undertaking a revision of the Energy Taxation Directive, and also is thinking about introducing a carbon border adjustment mechanism. So both could be two important initiatives to foster the development and deployment of solar fuel technologies in the future in the EU. With this, I would leave the floor to Deepak Pant for the final speech before the conclusion by the European Commission. One important piece of information: there will be no Q&A after the speech of Deepak, but Deepak has agreed to answer your question, if any, in written form. So feel free to type them in the Q&A, and Deepak will take care of answering them during the concluding remarks. So without further ado, I leave the floor to Deepak for this intervention on bioelectrochemical approaches for solar fuels. Thank you, Deepak.
Thank you, Felice and Joachim, for the kind invitation. So I was asked to give a high-level overview on the biochemical approaches. I have, as you can see from my slides, okay, I have to minimize, I think, this so that you can see the full screen. Is it okay now?
Perfect, perfect.
Okay, very good. So I have made the title of my presentation as Bioelectrochemical Approaches for Solar Fuels. And my name is Deepak. I work at VITO, which is the Flemish Institute for Technological Research. I am also associated with Capture, which is a center of excellence recently established at Ghent between Ghent University, Antwerp, UB, and VITO. I will give you a global overview, but before that, I just want to inform you the kind of work we are doing for CCU at VITO. So I belong to the electrochemistry team, and we are working on electrochemical CO2 conversion with a main focus on development of gas diffusion electrodes, as well as electrocatalysts that we are doing together with our partner University of Antwerp. We are involved a lot in design engineering of electrolyzers and their upscaling. By the end of this year, we will have a 2 kilowatt electrolyzer in place in a European project. And one of the main focus has been, as you can see here, is about the gas diffusion electrodes, starting from TRL 3.4, and now we can make them at TRL 7, which means the consistent and in the sizes going up to meter square of electrode surface area. A patent was filed, which they published just today. I received the mail. And we have a pilot production facility, as you can see here, very small pictures. And we also do industrial stacking, like I said, and colleagues are busy with downstream processing at TRL 7. Apart from that, we have a biotechnology team in our unit who is working on gas fermentation. In the past, they have been working a lot on biopolymers, which means bioplastics such as polyhydroxyalkanoates and butyrates production. And the technology is TRL 5.6 and has been shown at scale and has been proven both with the real off gases coming from the industry. Our colleagues are also busy with algae-based approach, but not on growing and bioprospecting, but more on harvesting and biorefinery. So downstream processing, taking out the chemicals and nutraceuticals from them. Our colleagues from Sustainable Materials have already developed and commercialized a technology on carbonation, so where they capture the CO2 in the steel slags, and it's now licensed to a company called Orbix, and they make carb stone as a stones which you can use for making footpath and dikes. And the first example was recently in Ghent, where a pavement is being built using these carb stones. In all of these approaches, we always couple it with the techno-economic and life cycle assessment. As you heard, it's so important to analyze the impact of these technologies. And as ambition for ourselves, we have a goal to establish a demonstration plant by 2022 to calculate the economic feasibility of the CCU approach. Finally, last word on this slide, VITO is a founding member of CO2 Value Europe, which is an organization based in Brussels and which is pushing the agenda of CCU with policymakers and the governments as well as the European Commission. And we are also busy with direct air capture, and I will just show you because we have this advantage of having geothermal facility, which VITO has been working on for more than a decade. And now we have a pilot facility. As you see here, these ventilators are available for direct air capture. I will not go into detail of this technology. So globally, I come to this approach for CO2 conversion. You can have them in either a reductive way or non-reductive way. Non-reductive way are the conventional ones, well established, like going for food and beverage, fertilizer production, enhanced oil recovery. They are more mature, closer to market, in fact, already in market. The only drawback, I would not call it a drawback, but the thing is they don't allow you enough opportunity to utilize renewable electricity. On the other hand, you have the up and coming approaches, as you heard since this morning, either electrochemical, bioelectrochemical, plasma, or thermochemical at different levels of development. And this is the direct approach, which allows you to use electricity, also renewable from solar, to convert CO2 into fuels and chemicals. So we have a project now with an oil company in India called Indian Oil, and we are trying to develop one of the pilot microbial electrosynthesis schemes, and they are also working on biohybrid systems using our electrodes. And we made an overview of the development that have taken place in recent years on material microbe hybrid systems. The article is still in press, but it's amazing that the kind of developments that have taken place in last 5 years alone, and the common concept of artificial photosynthesis or bionic leaf In some of these reports, the references are available in the publication. They are already exceeding the theoretical maximum of C3 and C4 photosynthesis, especially for solar conversion to isopropanol starting from CO2. So the two important aspects here are indeed the catalyst material itself, as well as the biocatalyst, the bacteria or the enzymatic system that is used to carry out these conversions. Now, this is a global overview of a multi-step electrobiorefinery, so to speak, that was published recently. And what you see here is different approaches that can be carried out. So the first one is, of course, a lot mediated via hydrogen. And the oval circles that you see here are the routes where the biochemical pathway takes place. So one of the popular ones is indeed the CO2 to formate approach, where CO2 is first converted into either formate or formic acid. And then this is used as a feedstock to further upgrade into pyruvate, polyhydroxybutyrate, single cell proteins, isobutanol. You can also have a syngas platform to convert CO2 first to CO, and then non-biological is Fischer-Tropsch, but also fermentation going to ethanol. Power to gas is an emerging application, and I will tell a little bit more about it later. And of course, the most common application of microbial electrosynthesis is indeed to produce volatile fatty acids and then further up concentrate them via chain elongation or electrofermentation into alcohols and higher hydrocarbons. Yeah, so this is an example. I just to give you an example, this is all not restricted to lab only. So there is a company in Germany called BFAB, and pardon this German slide, we wrote a chapter with them, which is in German. So the idea is the same that I mentioned just now, using renewable electricity to convert CO2 into formate, and then using formate either with wild type bacteria or genetically modified ones to produce animal feed, chemicals, or fuel. One of the most famous companies in this whole area is LanzaTech. Everybody has heard about them. They are doing great work already in the field business for quite many years now. And this is coming from a paper they published recently about their activities. So their system is based on these kind of feedstocks, industrial waste gases, syngas, carbon dioxide, which they take into after some pretreatment into the fermentation system. And they have a wide repertoire of genetically modified bacteria. And eventually their target is also to go to the fuels. They recently established this company called LanzaZ, and the intention is to go to make jet fuel starting from CO2 coupled to renewable electricity. Also, their process is quite selective. So this is a syngas, which is coming from municipal treatment plant, and over time, and as you can see, it's quite selective, and the main product they make is ethanol with the traces of volatile fatty acids and butanediol. Now, in our idea, this is our vision of a microbial electrosynthesis-based biorefinery. And the two things, like I mentioned previously, is about the development of the material, which means the electrode, where the bacteria can attach and grow biofilm, or also produce hydrogen. So this is a tubular electrode concept that we proposed with our collaborators from KAUST. And here it allows it has two benefits. One is the supply of CO2 in an efficient way. And the second one is by applying a potential, you can also generate hydrogen, which is then immediately consumed by the bugs in the system. And then you can also go to the same pathways, which I mentioned earlier, starting from VFA or methane. And this is the closed circular economy cycle in which no CO2 escapes from the system, and everything is consumed, and it's a closed example of a circular economy. We have also been working a lot on gas diffusion electrodes, like I mentioned earlier, and the main emphasis there is to use different types of catalysts, be it enzymes, bacteria, or electrocatalyst. The main advantage here is it's a three-phase system. So what you see here is a gas diffusion layer, which is completely hydrophobic and allows only the gas to go in one direction. Then you have the catalyst layer, where the bacteria can grow and attach biofilm. It could be carbon in most of the cases when we are using bacterial systems, but in electrocatalysts, it could be metals as well, and a current collector. And this provides the ideal three-phase boundary for the CO2 to be reduced. Another advantage of using it is the efficient mass transfer and overcoming the mass transfer limitations of supply of CO2 to the catalyst. And we saw that when we go from a direct sparging through a needle to a GDE, we almost double the KLA for CO2 dissolution. There is a lot of information we have put out in public domain about how we make these electrodes. So you can go to these publications or this YouTube link, where I have explained a little bit more about the electrodes and how we make them. Now, how does this efficiency of different electromicrobial production systems is, and especially starting from solar power? This is a very interesting paper that came from Cornell University 2 weeks ago by Buzz Barstow and his team, and they compared two routes. So one is indeed, like I said, the mediated one, where the hydrogen transport is the main energy carrier, and the second one is direct electron transfer, in which the bacteria is either directly attached to the electrode surface, and there is no loss of electrons per se. And then they calculated at each step of the biological cycle how much energy is lost during this process to go to the same molecule, in this case biofuel and butanol. So this was their algorithm. It's publicly available, and what come out of it is they came out with 10 different routes that are possible. So one is indeed the enzymatic fixation coupled via hydrogen. Second is direct electron transfer, and then third is again the CO2 to formate platform. Most interestingly, with the small alterations, so you can either genetically modify your bacteria, and they are already reaching the efficiencies exceeding 50%. So that's quite interesting, and this is a large amount of data in this paper. So if you are interested, just go through it. Now, compared to the techno-economics of microbial electrosynthesis, our colleagues from Delft University recently came up with this paper. This is about the sensitivity of the production per ton of volatile fatty acids or alcohols. So the red line is the baseline, and as you can see, electricity has a huge impact on the production cost. So if you assume that the cost of electricity goes from let's say 0.07 to 0.03 kilowatt euro per kilowatt hour, then it leads to almost 40% reduction in the cost down to 1,043 euros per ton. There are other factors that are also come into play, but this is one of the biggest influencing factors. In terms of CAPEX, they divided into MES assets and MES reactor performance, and only three main parameters are described here is the electron distribution. So how much of electrons can you get into your final product, Faraday efficiency, as well as the current density. And apart from these, you have the material cost, and they concluded that anode has one of the biggest influence on the capex of the whole system. The last point I wanted to cover was about the power to gas approach. The reason is this is relatively more mature compared to other approaches that I showed earlier. And this is the idea that in terms of when you do anaerobic digestion and produce biogas, you have a mixture of methane and CO2 and other gases. And the idea is to convert this residual gas again back to methane, so that to have a very highly efficient system. So this is an approach which is shown here, in which you take the biogas by application of electricity and electroactive bacteria. This residual CO2 can also be converted to biomethane, and the residual streams can go for resource recovery. In Europe, there are two main companies who are working in this topic. One is Kraite, based in Austria and Italy, using the same approach, and Electrochemical from Germany. And Electrochemical recently got a very large funding from European Investment Bank to upscale their technology. I think they are already at TRL 7 or 8 at this moment. So what are the top technical barriers and areas for future of bioconvergent pathways? So you can see I covered two areas. One is about the bioelectrochemical, and other one is gas fermentation. Gas fermentation, the one approach of LanzaTech is more mature. As you can see, it's a TRL 4 to 7, whereas bioelectrochemical is still lab restricted to lab only. Both have their advantages, but both still have a lot of challenges to overcome as well before they are commercially successful. So if I can conclude my very short overview, I will say that the technology of microbial electrochemistry have a lot of benefits. One is, of course, the renewable energy storage, CO2 utilization, but then it can also be combined to organic waste management, because if you can do the organic oxidation at the anode side. The cathodic microbial attachment is expected to increase the electron transfer efficiency, but at the moment it is restricted by the low current density. And as I showed in the slides, at this moment, in terms of capex, anode material and electricity consumption have been identified as the main challenges for their economical feasibility. And even if they are not viable in current state of the art, by improving different aspects, including the materials, electrode materials, reactor design, biocatalysts, you can have a positive net present value and profitability of these systems. And it's often asked, how do these microbial systems or microbial electrolyzers compare to CO2 electrolyzers? The one major advantage that biosystems have is about their long-term continuous operation. So most of the CO2 electrolyzers have been reported mainly for hours or at max few days, and we ourselves have run these systems for longer than a year without any drop in performance. But of course, this still need to be proven on real scale and industrial conditions. And like I said, we have a microbial electrosynthesis pilot already ready, but because of Corona, the implementation got delayed, but hopefully we will have some results from it real soon. That's all I have to say. And I was told there are no more questions allowed, but I will be happy to take your questions even afterwards. You can write to me directly or inform the organizers and they will let me know. Thank you very much.
Thank you, Deepak. Thank you. Before leaving the floor for the concluding remarks of the first session to Thomas Schlecker from the European Commission, I would like to thank on behalf of CEPS and on the study team all the panelists. I believe it was a very interesting technical session. I also would like to thank the attendees. And I remind you that we are going to have the second session of the day this afternoon at 2 o'clock, where we will focus more on the economic aspect of the solar fuel value chain. So thank you again for participating. And Thomas, here you go for the concluding remarks.
Yes. Can you hear me again?
Yes, Thomas.
Okay. So this is a difficult task to conclude because I have to, of course, let's say, agree with you that there's a lot of fantastic material and presentations. I would really like to thank all the speakers in this session. And I think there's a lot of interesting technical material, and I'm looking forward to look again at the presentations. So now what do I take as conclusion from this? I would actually like to start to, let's say, bring together the keynote speech from Sophia Hausener and the high-level speech from Deepak Pant. Now, one was Sophia introduced us to the conversion pathways and the scalability and the importance of techno-economics and having a life cycle analysis to be able to bring technologies ahead. And it was shown a very good example about how their own technology development moves ahead as a scalable device for hydrogen production. And then Deepak at the end now showed us basically what beyond hydrogen, what are other interesting, let's say, products if we look about bioelectrochemical approaches, electrochemical CO2 conversion and gas fermentation, the importance of hybrid systems, so including biological systems, and the importance of platform chemicals maybe as also important ways for commercialization of solar fuels. Now in this, there was basically embraced 3 presentations from Joachim John, Alessandro Venturin, and Andrea Leoncini about of course, the chemical pathways. We've seen here the importance, which is also true, of course, for the other technologies, of stage gates and how we basically have certain steps to be fulfilled to move ahead on the pathways. We've seen here, without not going again into the detail of the technologies, that indeed we have here a set of different TL for the different chemical pathways. And indeed, there are good arguments to move all of them ahead, and there are different challenges and opportunities for these different technologies. The same is true for thermochemical pathways, what was presented by Alessandro. Also here, we've seen that the timelines can also be different, what will be available at what stage, and in particular that not all components are at the same TL. Here I noted, for example, the importance of developing further absorbers and redox materials for thermochemical water splitting. Andrea also showed for the biochemical pathways that we have different technologies for biohybrid systems at very low level, but also microalgae, where we have different challenges and opportunities. So good arguments for all these different technological pathways. Now, coming to the questions, I think there was really a focus now on the importance of costs. This was based on the question on hydrogen, and also basically what we see as policy support needed, but also the importance of international cooperation. I think this is not only seen where one region is behind another one on the world, but it is actually because excellence, I take this away from this session, differs in different essential components in different parts of the world, so there can be a win-win situation for cooperation. So that's my, let's say, conclusion of this session. Once more, thanks to all the speakers and attendees, and looking forward to an interesting afternoon session. Bye.
Thank you, Thomas. So now it's time for lunch, and we'll meet again in about 1 hour and 20 minutes. Thank you to everybody.